All right, I'm going to start with the book problems. And I'm going to go through all three of them because I've got to tell you that in first period today, they requested me to go through the third one after I went through two of them. And I'm going to take this, copy, paste. Now I don't have to erase stuff. All right, so 15, 16, and then 18. Here we go. 15 will be first. Okay, get out of the way. Actually, how about I just turn you off? There we go. All right, 15. You want to realize that if you're going to get a natural log function going, you're going to have to integrate the known geometric power series. But before you do that, you need to make the denominator of the geometric power series be 5 minus x. And actually, would one of you mind closing the door because the echo, I don't want my voice echoing through the hallway. It disturbs the other classes. And thank you so much. And then on top of that, any noise, oh, it's ridiculous how much noise will echo straight up the stairs. Okay. So here's what I would recommend doing. First, notice that you have a 5 where you begin with a 1. And I warned you yesterday that that is the key place to start, is making your number be that 5. And what you can do is you can make this become that number 5 without changing the function you're working with by multiplying the numerator and denominator by 5. So that means that you don't even have to change the power series, and it is automatically going to be this function. And then I'm going to write down what that's equal to. So this is still the power series that we've been working with. Now, you realize that this needs to be just x, not 5x. So through substitution into the x, what do you need to substitute in? X over 5. Good. Oh, Jackie's back online. What? I couldn't hear you. I don't know. I don't know who got it first because I've got all these. Wow, it matters who gets it first. Oh, Jackie says I think I did. Oh, rigged. All right, so I'm going to write down the first thing that I need to do. I need to substitute into x over 5. And when I do that, and again, this is the first thing that I am doing to my power series. And I'm just going to overly write down what I'm doing because you want to take a good look at what that manipulation did. How did it change the function? And it's best to map out how is this function changing and get it to where you want it to be, and then go forward with your power series, because nothing is more frustrating than getting to a last step and realize that you did it wrong and you did all that work to your power series? No. So this is my big first step. Then I take a look at it, and I can either choose to take care of this extra 5 in the numerator now, or I can wait. How about this time we wait? And my denominator is what I need it to be, so let's take the derivative. So I'm going to write down that this next big step is derivative. And you need to take the time to think about this derivative. I'm going to rewrite 5 over 5 minus x as 5 times 5 minus x to the negative 1 in an abundance of caution, which is a phrase I've heard quite a lot lately. And then think through the derivative. So I am getting 5 times negative 1, and then blah to the negative 2. Chain rule says shove that baby function in, multiply by the derivative of that baby function, and then let's look at what that gives us. That gives us 2 negatives make a positive 5. Oh, you know what? Do you see what I did wrong? Yep. Supposed to integrate. This is why you don't do your power series first. I don't know. I just had the wrong thing in my head. And I actually need to integrate. So here we go again. Integral of 5 over 5 minus x dx. Do the u substitution. Make sure you are cautious about what you are getting. So I have this 5 constant multiple, and then I have negative du replacing the dx, 1 over u, and I'm integrating. Now, normally you need absolute values, but if you take a good look at the interval of convergence that you're working with, you'll see that that particular domain does not require the absolute value. Then I need to, technically there's a plus c, but you can choose to write it now or write it later. Right now I'm going to not worry about it. I'm just going to try and get to an answer here. U was a 5 minus x. And I want to look at, is this the function that I intended to get? And the answer is no. I need to divide by negative 5, and then I'll be good. Now, if you had in a previous step decided to divide by 5, you could always just go up there and say, and make it negative 5. And it works out perfectly fine. But by doing that, you now have the function you intended to get. So now I'm going to go through that process with our power series, and in the meantime, also be talking about the interval of convergence. So I'm going to start here with the known series and the first few terms and the general term. I'm going to substitute in the x over 5, and I'm going to distribute the squaring between the x and the 5, and distribute the cubing and then when I plug in x over 5, I'm going to also separate the x from what it's divided by. Because if I don't do this, then when I integrate, I actually have to go through a u substitution with the power series. And most people are going to not notice that or do it incorrectly. So that's my big warning to you. That's why I've actually been telling you to simplify your these power series so that you don't have x multiplied by anything. That avoids the u substitution issue when integration comes up. So then I am getting to the point of being equal to this series that I have here. But when I'm solving an indefinite integral, this is where I'm getting that plus c. So I've got c plus, and then integrate x squared over 5 times 2, blah, 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 blah. Add 1 to the exponent, divide by that exponent, and then 5 to the n in the denominator is a constant multiple. And then divide by negative 5. So if I divide by negative 5, I'm going to end up with this equation equaling. Now, I'm just going to go ahead and divide the unknown constant by negative 5, but I could just call it a new unknown constant. And I don't like having to write more than I have to write, so I'm going to do minuses instead of plus negatives. And again, I'm dividing by 5 now, so I'm going to write a bunch of minuses. And then divided by 5, divided by 5. Apparently, I can't help myself but to write a plus. And then minus, and I want to emphasize that the formula is minus. I think maybe the best thing I can do is do plus and then write a negative 1 to emphasize that that actually is part of the formula. And some people are going to look at that n plus 1 and go, I don't like that, and just make that n. That's fine. It just changes what your starting n actually is, and you can feel free to do that. I need to find my unknown constant c. Or perhaps I should just say, I need to figure out what that big mess of an unknown constant is. I can find out what it is if I plug 0 in. So realize what I'm doing is I'm actually going to call this a c sub 1 because I really don't want to have to deal with the extra division there. I want to find my c by plugging in the center of the polynomial. And hopefully you see that the center is 0 because all the x's are just two powers. They don't have addition or subtraction to them inside the powers. So when I plug 0 in to the left side, I get the natural log of 5. On the other side, that's equal to this big giant unknown constant c sub 1 minus 0 forever. So this time I actually do get something for that c, and I can now say that the natural log of 5 minus x is equal to the infinite series that begins with the constant natural log 5 and then has all of these terms. Ooh, you know what? I've got lasso. Oh, yeah, that's right, I turned you off. So I'm going to use my lasso because I'm tired of writing. Whee! Oh, I already had that one, didn't I? That's okay. There's my fix. Woo! Okay. Now, interval of convergence. Realize that if you want to, you can just slap the ratio test onto this formula and check the endpoints, and you'll get the interval of convergence. Let me tell you that you can be aware at the same time, or instead of that, you can be aware that the original series, the interval of convergence is -1 to 1, not including endpoints. When I substitute in that x over 5, that makes my r for a geometric series be x over 5. So if the absolute value of x over 5 must be less than 1, then I'm dealing with this converges for x being between -5 and +5. And at that moment, the interval of convergence does not include endpoints because it's still pure geometric. When I integrated, I had to check the endpoints. So let's check those endpoints, and then hopefully you realize that dividing by -5 is not going to change the interval of convergence. So I have for my interval of convergence on the official answer that it's either open or closed, -5 to 5, open or closed. And I can plug the x's in where it's at, and actually it would be better to plug them into this formula because I've got these nice little n+1s sitting around that are all the same. So when x is equal to -5, yeah. Oh, okay, the radius of convergence is 5, and I guess that's all they asked for, huh? Will I ask for interval of convergence on a test? Yes, I will ask for interval of convergence on a test. So for your homework, you actually only had to get to r equals 5. Let's take a quick look and see what this ends up being, and that'll help promote all the other stuff we have to be practicing. So I'm going to plug the -5 into x. And again, you didn't have to do this on your homework. I can see really nicely that what I have is an alternating series. I'm looking at this one, an alternating series, and it compares to the harmonic series. So alternating harmonic does converge. And I can do that through the alternating series test. When I come over here to this one, realize that this little negative, ooh, did I accidentally? I did. I messed up. How did I mess up? I accidentally put an n there and it wasn't there. It's not an alternating series. Therefore, it compares to a harmonic series and it diverges. Over here with this one, this -1 is just a -1. These are going to cancel and leave me with a -1 to the n+1. This one is an alternating series. And so it will converge by alternating series test. So if I wanted to do the interval of convergence, I now know that it converges at -5 and diverges at 5. And so that's the end of that problem. Woo! 1 down, 2 to go. 16 is next. And yesterday I told you, make sure that you look first at that denominator. If you have a parentheses to a power, it's very likely that you're going to start with the geometric power series. You're going to make the denominator become this denominator, and then you're going to take its derivative. The numerator will only come into play after that's all been done. So let's make this plan. We're going to start with a 1 over 1 minus x. To get this blue denominator, what do I need to do? Substitute x with 2x. So I'm going to do that to see that that is what I get. And that is what I get. So once I have created that denominator, next step is to do the derivative. This time I do get to take the derivative. Ha ha ha. But I need to be careful and think about what the derivative is going to be. So I'm going to set it up where it's a -1 exponent. And then using the chain rule and the power rule, negative blah to the -2, baby function. Shove it in, multiply by its derivative. And then let's take a look at what that gives us. I have 2 negatives and a times 2, and the 1 minus 2x is squared in the denominator. Now the function I'm trying to create is the same function, but with not a 2, but an x cubed. So you know you need to use the derivative when you have a situation of your denominator has this linear function in the interior and it's parentheses with a power on it. If you need to get a logarithm or an inverse tangent, you're going to integrate. Come on. Oh, I think I see the key. I have to actually touch the screen again, and then it goes, oh. Oh, no, does that mean my computer is like me? I'm easily distracted, and I think that's what it seems to be doing. So, in order to get finally what I need to make this, I'm going to multiply by x cubed divided by 2. And when I do that, this will become x cubed. Was it a squared up on top? I don't have my glasses on. Okay. Shoot. You can see why I didn't give you 17. You're right, that is a squared. Oh, that was already 2. Doop, doop. Yay. And so that is what we were needing to get. And I think they were telling me, yeah. Okay, I've got a plan. Now it's time to execute that plan. Yeah, maybe it's just you spacing out. My computer goes dark because it's stopped thinking outwardly. least that's my opinion. All right, get that out of the way. And now I began with the power series. And you know what? Since I'm doing derivative, how about I just do a big old sigma on this one? I don't have to deal with a plus c. So from 0 to infinity, x to the n is my formula. It converges from -1 to 1. If I substitute x with a 2x, I'm going to look at the fact that I need to distribute the n exponent over the multiplication. And what I'm doing is I'm changing my radius from being x to being 2x. So absolute value of 2x less than 1 will cause converge. That means that between -1/2 and +1/2, I will get converge. My radius of convergence has now changed to 1/2. Then the derivative must be taken. The constant multiple stays, and then the derivative nx to the n minus 1. The radius of convergence will not change with the derivative, but I might gain endpoints with the interval of convergence. Now, if I decide to leave this at n equals 0, do take a good look and see that plugging in 0 actually gives you 0 for your first term. If you left it this way on a test, I would give you full credit. The simplified version would be to take out the 0 first term and just have it start at the next one. Then multiplying by x squared over 2 will not change my interval or radius of convergence. And let's see, so if I'm dividing by 2, then the 2 is going to be to the n minus 1. And then I am multiplying by x squared, so that's going to be add 2 to the exponent to become an n plus 1 exponent. And there is my formula. If I want to know for sure the interval of convergence, I can plug in the -1/2 and the +1/2 and check. Do you want to see that done, or do you feel like see it done? Yeah, let's just go ahead and do it. We're going to check the endpoints, and that will help us to continue practicing using all these different tests. So x equals -1/2, x equals +1/2. Now I'm going to do something to make my life a little bit easier here. I would like these exponents to match. That will make my life easier. So to make them match, I need to divide by 2 squared and multiply by 2 squared. Multiplying by 2 squared will add 2 to the n minus 1. Then when I combine these two, that will combine to make a -1 only to the n plus 1 power, and then 2 squared is 4. On this one, these two are just going to make 1, And on the second one, you might see a little bit better that is severely diverge. That nth term test for divergence is just laughing at the fact that this bothered to show up to ask, do I converge? In fact, its A does not exist. And so it diverges by the nth term test. And then if you take a moment to think about it, making that an alternating series is not going to help the situation. Diverge by the divergence test as well. So the interval of convergence is open interval -1/2 to +1/2. All right, 2 problems down, 1 more to go, and then we can hit the multiple choice questions. Okay. Arctangent of x/3. I'm just going to bring that down and write it. Okay. We will be starting with 1/1 minus x. We are wanting to integrate, and when we integrate, we end up getting arctangent. There are a couple of different approaches you can take. What I think is going to be easiest is if I create somebody who will integrate to make just plain old arctangent x and not worry about the divided by 3 for the moment. So I need to substitute into x a negative x squared. That'll be my first step. Then if I integrate this function, can you just automatically use divergence test? Are you talking about like the previous problem? Past question? Yeah. Yeah, the divergence test just worked. Yeah. Oh, did I just suddenly? Never mind. Trying to pay attention to chat, sometimes I don't read it until 5 minutes later. Okay, integrating this function, I know that gives me arctan x. There is a plus c, but I'm going to let the polynomial handle that end. This is not the function I wanted to get. I wanted to get the arctangent of x divided by 3. So at this point, I can then plug into that x/3. And we could have dealt with this before integration, but I've got to tell you, it is far better to deal with after integration. So now that's the plan. So let's go. With this being integration, I want to keep a few terms to deal with the end bit of finding the plus c. So I'm starting with 1 plus x squared. I'm going to call that enough. Then substituting in a negative x squared. The negative will square. And here I'm going to separate the negative sign with the x squared, and then use my exponent rule of x squared to the n is x to the 2 times n. And then my next step is to integrate, but when I'm integrating, I am getting a plus c. So I'm going to write down that this is equal to c plus, and then I'm going to start integrating. Now, I can actually solve for my plus c before I move on to the next step. Anytime you need to find your plus c, and due to the fact that you're trying to create a very specific function, you can find your plus c by plugging the center, which is 0. Arctangent of 0 happens to be 0, and then it's c plus a bunch of zeros. So c is 0. Bye-bye, c. And now I'm going to plug in the x over 3, and that'll be the last thing, and we'll be done. So x over 3, I didn't need the parentheses, I just did. And then minus, I'm going to go ahead and just not simplify it right now. And just to emphasize the simplification, I have x to the n plus 1 divided by 3 to the, I have x to the 2n plus 1 divided by 3 to the 2n plus 1, and then the rest of the formula. And that would then be the simplified version of that formula, but that's it. As far as interval of convergence is concerned, the only thing that could have changed it, the radius anyway, was plugging in the negative x squared. Oh, the plugging in x over 3 can change it as well. You can always throw out the ratio test on this if you need to, but I'm going to quickly say that the negative x squared does not change the interval of convergence. That's still negative 1 to 1. The integration might add in endpoints, so those need to be checked. When I plug in x over 3, I can think of it as my radius is x over 3, but yet it's not quite geometric anymore. But you're looking for when this is less than 1, but it might diverge at the endpoints because this is not pure geometric. You can use that to help you see that it's negative 3 to 3, or perhaps you see it another way. The endpoints would need to be checked to determine the full interval of convergence, but your homework didn't ask you to do that, so you can just say radius is 3. And if I check this, I think it's going to be easiest looking here. That negative 1 to the 2n, was that supposed to be 2n? No. Did you guys notice I did that? Yeah, that was a mistake because I just got happy with the 2n. There's n. This was supposed to keep the n. Silly me. But I didn't notice it until I had to go to interval of convergence and saw, oh, wait, no, oh, oops. All right. So negative 1 to the n, 2n plus 1. When I replace x with a negative 3, I am getting a negative 1 to the 2n plus 1. But 2n plus 1 as an exponent is just saying, hey, negative 1 will always be there. But I do have this, making it an alternating series. And it will converge. For the other one, I basically get the same thing. When I bring the positive 3 in here, this just becomes a times 1, but it's an alternating series, and it converges by AST. So final answer is interval of convergence includes endpoints. All right. Now let's go over to multiple choice. And I'm going to start off with problems that I recall were asked to be looked at by the previous class. And then with any remaining time, I'll do the rest of them. And how are we doing on time? We have 10? Okay. Which of the following series diverge? Number 3. That one is definitely a little bit tricky with that sign, or no, wait, hold on. This is not the one I meant to do. Did you want me to do this one? I was thinking about something else. This was the one I was thinking about. Number 5, which of the following series is conditionally convergent? Oh, someone asked to do 3. I'll go back and do 3. Remember that conditional convergence, that means if I take the absolute value and I look at what I have, that series diverges. But if I look at it as is, it converges. When I look at sine n over n, or over n squared, I know that its absolute value is less than or equal to 1 over n squared. And then I'm going to get absolutely convergent because I had to absolute value those and see that it's less than a p series. So it converges, but it's not conditionally convergent. The other 3 have negative 1 to the n plus 1. When you run into conditionally convergent, most likely you are dealing with an alternating series, where the alternating series test is going to tell you converge, but when you absolute value it, you get diverge. If you look at D, do you see that D is geometric? Geometric series are never conditionally convergent. So that's out. Then I turn to the last 2 and I look at the key difference. I've got an n over root n and a root n over n. If I simplify what I want to realize is going on is B is asking you if the square root of n as an alternating series converges, diverges. Do you see that alternating series test will say I can't be used? You turn to the divergence test, and the divergence test says, oh, your limit does not exist. You're growing and also alternating. You are diverged completely. And then finally, we look at C. If I absolute value it, I get a P series where P is 1/2, which is a diverging P series. But if I bring the alternating issue in, it will converge with the alternating series test. So woo, we've got a winner for conditionally convergent. I'm going to go back and look at number 3. Oh, you're a tapper. I'm distracted by tapping. I'm distracted by just about anything. So it's frustrating. I need to figure out what number is this, but maybe I don't need to know exactly what number it is. this is a geometric series. I only need to know if that number is between -1 and 1 or not. Sine will at best be less than or equal to 1. For sure. You know that inequality. So if I take something that is at best 1, maybe smaller, and I'll throw in absolute values around it just to push the issue. I am dealing with a geometric series where the r is 1 over pi or smaller in its absolute value. So I have something that is converging. It is a geometric series that will converge. And it's mostly because this is at largest 1 divided by pi. Now, on number 2, oh my goodness, p series. Diverge. My p is 1/3, which is a diverging. So that one's in. For number 3, if you think about the limit as n approaches infinity of just the formula, which is what the nth term test looks at, I get 1. That's not 0. That diverges. So 2 and 3 are my diverging series, but 1 does not. It converges. Okay, I am going to move over to number 6. For number 6, you want to know what values of p causes both to converge. So looking at this first one, you've got a p series. You need that exponent to be greater than 1 in order to converge. I think it's a little bit cruel that they're using the letter p and then all of a sudden it turns into a geometric series. It's like it's trying to trick you, and I hate it when standardized testing thinks it's tricking you. Anyway, the variable of sigma is n. I want to point that out so that you can see that you are dealing with a geometric series. The variable is the exponent. That p is just some number, and you want to know what number works to make it converge. So that means you have an r is p over 2. The ratio, or not ratio, the geometric series test tells you that as long as the absolute value is less than 1, you will get converge, and you know you will diverge at equal to 1. And so that gives me absolute value of p must be less than 2. Now I need and both to work. I prefer to do a picture drawing on a number line and see that absolute value of p needs to be less than 2. And then if I include 1/2 is somewhere around there, has to be greater, can't be equal, I get between 1/2 and 2, does not include 1/2 or 2. And that gives us C. Ooh, this is a pretty one. Isn't it lovely? Okay, let's get going. This says specifically the alternating series test can be used to show convergence for which of the following series. We're going to focus on the formulas. For this one, you don't have to use alternating series test to determine converge, but you can use alternating series test to show converge. You're good to go. For the next one, it's got sign in it. Danger, danger. The sign of a number, if you keep throwing consecutive integers at this, it's going to be positive for a few terms and then negative. It's not going to alternate. between negative and positive. That sign N makes this not an alternating series. Even though they make it look like it might be, some of these signs are negative. This is out because I cannot use the alternating series test to show convergence. It's not asking if it converges, it's asking if that alternating series test can be used to show it. And then when I hit the next one, I notice that this says evens and this says odds. The even terms are negative, the odd terms are positive. Yes, it is an alternating series. And if you look at the formula, the limit is 0. But what does not happen? It does not strictly decrease. To use alternating series tests, that has to be decreasing when I take the absolute value, and it is not. I cannot use alternating series test to determine its convergence. Now, the bell just rang, and you guys need to go to class. Leave your nameplates there so that I can take attendance correctly. 246, okay. And then I'm going to keep going for those of you who want. Do you want me to do all of these problems or just the harder ones? Okay. I'm trying not to trip this time. I didn't trip. Okay, to finish up these problems, number 8, which of the following is a convergent P series? This one won't take too long. This diverges. This is a geometric series. This is a P series that diverges. And when I come together with this, and I simplify, this is the square root of n cubed in the denominator, which means it is n to the 3/2 power. 3/2 is greater than 1. That is a converge for a geometric series, or not for a geometric. That is a converge for a P series. There we go. Now, number 9 definitely needs to be looked at. And this didn't print properly. These should be D's for the dx's. And this is saying the integral test can be used to determine that which of the following statements about the infinite series is true. So again, this says the integral test can be used. And you're trying to figure out which is true. Now, as far as the integral test goes, the concern is converge versus diverge. So if I'm able to get an answer to the improper integral from 1 to infinity, it's a converge. If I'm not able to get an answer, then it's going to be a diverge, and that's really about all there was to it about the integral test. What you're really trying to do is just determine what is the answer, if there is an answer to this limit or to this improper integral. What I'm going to do is first change it to a proper integral by changing the infinity to a b, and look at the limit as b approaches infinity. Then I'm going to separately take a look at an indefinite integral with the same function. I'm going to integrate if I use a u substitution for the exponent on the e. The derivative is negative x to the negative 2. And if I multiply the negative over to the du, this becomes positive, and I can see that the x squared dx is replaced with a negative du And then my integral becomes what's left over, e to the u. Integrating, I get e to the u. I put the u back in. And that is the answer. That was e to, make sure I get it right. That is the answer to the indefinite integral. I'm going to bring it back to the fact that it is a definite integral with a limit to be solved. When I plug in b, I get negative e to the 1 over b minus plugging in 1 minus negative e to the 1. If the b is heading to infinity, the exponent is heading to 0. So I'm getting negative e to the 0 power. Minus negative means positive e to the 1. And then you need to remember that e to the 0 is 1. So negative 1 plus e is the correct answer, and it does converge. And remember, when you're using the integral test, the integrand must be a function that has three things happen. Do you remember the three things? It needs to be positive, it needs to be continuous, and it needs to be decreasing. Now, I'm going to go ahead and go over the rest of the problems since I've got a little bit of time on my hands. Number 1 says the power series has a radius of convergence 2. At which of the following values of x can the alternating series test be used with this series to verify convergence at x? Well, if I'm going to use the alternating series test, then I'm probably getting a negative 1 out of this. 4 would make that a negative 1. And so if I plug in 4, I'm just taking a quick look at what I'm getting. Can I use the alternating series test? Yes. Is the absolute value of it decreasing to 0? Yes. So 4 works. Number 2, you are told if the series converges and a sub n is greater than 0 for all n, which of the following must be true? Key word is must. Now, if I take a good look at what this expression is saying, that's the ratio test. And we're looking at must be true. You know the series converges. You know that a sub n represents only positive terms. I don't have to get an answer of 0 from my ratio test. That's not a must be true. Then the absolute value of the terms are less than 1 for all n. For all n, definitely for n being larger, I think that doesn't look good, but I'll hold off and come back to it. C says that this is equal to 0. Realize that's saying the actual infinite sum equals 0. No. It's doubtful to be true. Now, if a sub n converges, does that automatically mean that if I multiply by an n, it suddenly diverges? A sub n could be a geometric series. If it's a geometric series that converges, that is still going to converge. That is not correct. Okay, now the next question. If I have a series a sub n, and it has positive terms only, and I know it converges. My next question is, if I do an inequality where I am comparing a sub n over n with a sub n who I know converges, am I looking at them both being positive? Yes. Is the inequality the way I need it to go? If I continue to make the denominator here bigger, I'm going to make the overall fraction smaller. So I have positive terms where they're all smaller than something that converges. Yes, this must converge by the the direct comparison test. And again, this B was kind of awkward, but it is that, yes, at some point, this is going to be true, but it does not necessarily have to be true for all n. And that's why E is the correct answer. We did 3, 4. Which of the following series converge? You want to notice that this is a P series where P is 3/2. That's a converge, yes. This is a geometric series where R is 1/3. It converges. And then this one. I might be able to figure out an inequality that will work with this, but I'm going to head over to the integral test, and I'm just going to do a quick check with the integral test. If I had to integrate this, I would do a u substitution of natural log x. The derivative is then 1 over x dx. That will cause this integral to change into 1 over u du. When I integrate 1 over u, I get natural log of u. I put the original u in, I get the natural log of u. And then if I'm trying to integrate from 1 to infinity using the integral test, then I'm going to be looking at, natural log of x. I'm integrating from 1 to b, where b is heading to infinity. As soon as I plug that b in here, and I look at heading to infinity, natural log of infinity heads to infinity slowly. Natural log of super slow infinity is still super, super slow infinity. It is heading to infinity. It does diverge. That one is diverge. So 1 and 2 only for number 4. Then did I do 8? Yep, that completes it all. Yay! See you another day. Ending recording.